Hi everybody and welcome to my lab. Today I thought we'd do something a little bit different. I'm working on a design and I could use a step-up converter. And so today I'm going to put something together. It's a prototype design, and so this may or may not make it into production, but it's something that I would like to try because I'm getting some noise on some lines, and I have available to me 3.3 volts. I also have 24 volts, but it's on the other side of the board, and it's complicated. But this may be a very quick and easy solution. And while there is some cost associated with this solution, it uh, happen to have all the parts here. So all I would need to do is actually make the circuit, and I could breadboard it or possibly have one of my Chinese manufacturing contacts build me some prototype boards, and I could populate the SMT. Uh, the uh, the the chip that I've decided to use is the MC34063. It's an ancient chip. It was originally developed by Motorola way back when. Um, but it's quite inexpensive. It's still in production, and why not? It does the business, as they might say. Now, I'm not the first one to do a video on this chip. I realize that Dave Jones did a bang up job on it, and hats off to him. He really helped me understand how it worked some time back, and hats off to him and his videos. Okay, but today I'm going to use it as a step up, and here you can see is a typical application for a step up converter using this chip. And the reason I like it is it's very simple. There's not a lot of external components, more than some uh, more modern chips, but this one's very versatile. And let me just kind of walk you through how this works. So your main voltage comes in here, and their typical application they're showing 12 volts, and then we go up through a current sense resistor. Okay, and that's what's being indicated here is this is part of the current limiting circuitry, and then we come in and we have this 180 ohm resistor that's being used to bias this Darlington pair. We then go through uh, an inductor, down through a Schottky diode, and back to well, not back to the output voltage source. Now, the way the circuit generally works, and I'm not going to get into a lot of the theory of that right now, is that the capacitor will charge up, and then the switch will turn on, and it will dump the voltage uh, out of the inductor and cause it to basically boost. Okay, so it's a matter of taking this bucket, if you will, and piling it on top of itself. Okay, it's a very crude explanation, but it's going to do for today. Okay, so in our application note here, there. Sorry, this is actually not an application note. It's the data sheet. They tell us that there are a few pieces of information that we're going to need, and so I just have a little spreadsheet here, and I'm going to, I'm not going to take a whole lot of time formatting it, but VSAT is one piece of information that we need, and so where do we find that? The easy way is search the data sheet. Okay, Control Find Saturation. Let's take a look at the first place that we find it. And because we're using the Darlington transistor inside, we can typically use the typical. And so we're going to be looking at 1 volt for this. Okay, and that's the first bit that we need. Okay, and so let's scroll back down. That looks right. Okay. The next piece of information that we need will be the output rectifiers. That's the Schottky diode here. And so we will call our VF. It's going to be, let's argue, 0.3 volts. The next thing that we need to do is we need to look at the following parameters. So we have Vin for me. Vin. For me, that's going to be 3.3 volts. My V out that I'm going to be looking at, I'm gonna set it for 12 volts now. That may change a little bit. The I out is a whopping 25 milliamps would be a greedy day. The frequency out, freak out. I'm going to say 50 kilohertz. Seems like a nice place to start. And my V ripple. Yeah, I could live with 25 milliamps would be a great day because of the application of this. I'm not too awfully worried. Okay, so now we can start getting into the formulas, and it looks daunting. It looks like there's a lot, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's only 10 actual calculations that we need to do, so it's not too bad, right? And so T on divided by T off is going to be our first calculation. And in order to calculate T on divided by T off, what we need to do is we will say that we need our V out. Okay, so V out plus the VF. Okay. Minus V in minimum. Well, where did they ask us for V in minimum? Oh, there it is. Ha! We should have actually got that one too. Okay, so V in minimum. V in, call it V min. For me, I'm going to call that 3 volts, which happens to be the lower threshold of this chip. All right, there we go. First mistake. Let's see how many we make. 1. Okay, so try again. So now my V out plus, where did we go? Plus the forward voltage minus the V in minimum. All divided by the V in minimum minus the V sat. And there we go. 4.65. All right. Fantastic. The next calculation is the T on plus the T off. This one's fairly simple, so this is just 1 divided by the frequency. Okay, so we're going to call that 1 divided by the frequency. Okay, I don't know why that gave me a hard time for a moment there. Okay, so now the next one that we're looking for is the T off. And T off is going to be equal to the T on plus T off. T on plus T off. That one. Divided by the T on over T off plus 1. Okay, really small number, yes. Okie dokie. Okay, moving on. So T off, T on. T on is equal to T on plus T off. T on plus T off minus the T off. Another really small number. Okay, and if you want to know, this is going to be in seconds, and so if we wanted to look at this in milliseconds, take this times 1,000. Still pretty small number. So let's go times. So this would be in microseconds. Alright, so yeah, the ratio seems about 4 to 1. Yeah, we can live with that. Okay. Okay. Next is CT. And CT is equal to 4 times 10 to the power of -5. It's a nice small number. Times T on. I don't know if that counts as a mistake. We shall fix it. There we go. Super small number. Okie dokie. So now we're looking for high peak of the switch. So this is referring to the peak current that's going to go through the switch. And we need to be careful of this. It's going to be a small number, but yeah, I'm not too worried about it. So 2 times the I out max times so the T on plus T on over T off, T on over T off. Shoot. This is equal to 2 times T on over T off plus 1. Okay, that does not seem right. Alright, 2 times the current is number 2 times that. That seems better. So you can see that the current actually goes up quite a bit. And if you think about how a transformer works, this kind of makes sense. We're taking 3 volts, we're stepping it up 4 times. So if I took 25 millivolts in, or wanted 25 milliamps out, I should say, I need to draw 4 times that current. And so you're into 100 milliamps before you consider any losses at all. All right. IP switch RSC. Okay, so next value RSC is going to be equal to 0.3 divided by the peak of the switch, which is that guy. Okay. Next is L minimum, which is your inductor, and it's important that you notice that it is the minimum. You can always go with a higher inductance. Okay, and this is kind of what we're driving at now. So this is equal to the V in minimum, V in min, minus the V sat, divided by the I peak of the switch all times the T on max. All right. And there's our inductance. So again, this is going to be in henries, and so this is equal to that times 10 to the power of 6. So this is in not milli, but microhenries. Okay, not too horrible. Next one that we would look at is CO. CO, which is the output capacitor, is going to be equal to 9 times I out times T on divided by the V ripple, peak to peak. Where'd you go? V rip. Okie dokie. And so again, this is going to be farads, so we'll do this times 10 to the power of 6 microfarads. That's a pretty beefy capacitor, but we'll circle back around to this in a second. And so now our V out, we're not going to worry about calculating that right now, because that's just going to be for the 2 resistors. But we can play around with that in a second. Now, like I say, this value seems a little bit high. This one's quite low, so we can start to play around with some things. For example, instead of 50 kilohertz, we could change this to 75 kilohertz, and you can see the inductor values change, and so does the output capacitor. And I maybe like this a little bit better. Let's just argue what happens if we go down to 25 kilohertz. Okay, so you can see the inductor gets larger, the capacitor gets larger, and you know, all just for the benefit of maybe a little bit less noise. The maximum that this chip can go to is 100 kilohertz, and you can see that the values drop quite a bit. Okay, but as the speeds increase, you also get more noise. You get a little bit more a little bit hotter chip, and if you're trying to push it, if you're trying to push a lot of current, then it becomes problematic. Um, I tend to run these a little bit lower, and I'm okay with 77. So we'll probably go with 100 microhenry and 100 microfarad on my output capacitor. I'm not going to worry about any filtering or output noise suppression other than the capacitor, because that's good enough, right? Okay, so that's probably enough to get started on the design. I guess we could take a moment to look at that voltage divider, the V out. Um, so now that we've determined that we're going to be about 12 volts, oh, maybe that's something else that we can talk about, is what happens if I am willing to accept a more output ripple. So if I increase this to 50 milliamps, for example, notice that my capacitor drops in half, right? My inductor is still the same. It's still going to be 78 microhenries, but now I can get away with a 50 microfarad capacitor. And so I know that 50 milliamps is going to be okay. I could probably live with 100 milliamps if I really wanted to. Um, but this is going to be something that I can play around with a little bit, is that output capacitor, and tweak it to the minimum that I need. Why wouldn't I want pure DC? There's a cost associated with it, and because of the application, I don't really care. All right, so let's take this back to my 25 milliamps, and there we go, 100 microfarad. And that's something that we'll be able to get quite small, especially seeing as the output voltage is only 12 volts. So I'll probably go with a 25 volt. Yeah, might cheap out and go with something smaller like a 16 volt um, capacitor. Okay, so we were going to look at the output resistors R1, R2. Okay, and they give us a nice little example here where we're looking at R1, R2, and basically it's just a voltage divider that we can work out the math on. We have V out. We're going to look at R2 is given. R2 is going to be equal to sure, 47,000 ohms. I like that. And so we're trying to solve for R1. Okay, so V out here, V out 12. Oh. Yeah, look at that. V out divided by 1.25. Let's actually use algebra. That's good. Okay. So that, lots of brackets because I'm paranoid with Excel, minus 1 divided by R2. Oh, shoot. 1 over all of that, right? We need to invert it. That's still not right. Like I say, lots and lots of brackets, and now it makes more sense. Okay. Scripting would be good. Working my formulas out ahead of time would be good. But maybe this kind of works out, because now you can see some of the frustrations that you'll probably go through in when you're trying to work this out for yourself. Okay, so 5.4K and 47K seems reasonable. Seems seems like something we're going to be able to design around. Okay, so I'm going to take this information, I'm going to keep it up here, and I'm going to start designing away. Okay, so let's get started on the design. So what I have here is just a blank design, nothing in here yet, no devices picked. I've created a DC generator at 3.3 volts, and we can start to pick some components out. And so obviously the first one that we're going to need is that 34063, and there it is. It's going to be the wrong package for what we want. I'll just pick the SO8 for now. But here we go, we can place that component. The next thing that we're going to need is we have a resistor, that current sense resistor, and you know the default for it right now is 0.22 ohms. So we can go ahead and let's just grab a resistor, res, like that one. Okay, and we'll place it over here, and we'll change it to 0R22. Okay, and looking at the data sheet, so our we need a capacitor here as well. It's not going to need a huge capacitor, but we'll toss something in. Cap. Okay. Yeah. Yeah, we'll go for the non-polarized for now. There we go. And I'm just going to take a stab at this. I'm going to say 10 mics are good. We're obviously going to need a ground reference in here somewhere. So there we go. Let's ground this guy. And so this goes into pin 6, which is our V positive. Okay. Our pin 7, which is the current sense, we'll grab here. And then we have a bleeder or a current limiting resistor. So let's grab one more resistor here. Okay, to pin 8 DRC, and this should be about 180 ohms, which is a nice value. You can get those easily enough. The next thing that we're going to need across the top is an inductor. I'm going to pick something called real inductor, and the reason for that is we can change quite a few of the parameters. Okay, for example, here we go. Let's take a look at some of this. We have series resistance, parallel resistance. Yeah, okay. We wanted to set that to 77 microhenries. So let's say 100 microhenries. Okay, and that goes from here around to pin 1 here. Fantastic. And right, we're going to need a Schottky diode. Diodes, Schottky, we'll just pick something generic for now. Diodes, Schottky, generic, diode dash SC. Obviously wrong footprint, but it's good enough for now. And we'll put that in series. And so this is going to go from here to our V out. So we're going to need another capacitor that's going to sit on our output. and we had determined that we wanted this to be about 100 microfarads. Now obviously that's not going to be non-polarized, so let's go back and grab another component, cap, and this time we want something that is polarized. Okay. And of course we'll have to ground that. And this is going to be our output. And so I'll just put a label in here for now, and we'll call this V out. Okay. Now, pin 2 goes directly to ground, which is fantastic. Pin 3 is the timing capacitor, and so that's the CT. CT we determined was going to be, let's get this in units we understand. So that times 10 to the power of 9. What? That seems a little bit small. Milli, micro, nano. Oh, yeah, to power 12. That's right then. So I'm looking at, call it 440 picofarads. So let's just grab this guy, give us a little bit more space. And we'll grab a capacitor for CT. We want that to be, where did we go? So 470 will be a standard value, 470 pico. Pin 4 goes directly to ground as well. Okay, and that leaves our voltage divider. So we need our 2 resistors. 1, 2, and the first one was 47K, and the second one we determined we wanted 5.5K. Go. And yeah, I mean we could use a terminal here so that we didn't have to drag this wire all the way over, but we'll call it good enough for now. And so that's looking reasonable. Let's give it a little test here, and we'll test the voltage out, and we'll toss in a load resistor just for now. There we go. And we're going to assume that we want just a fairly low current, so we'll just drive it with 10K just to give us some current draw. Alright, so fingers crossed, here we go. Simulating, loading up. And it's bouncing around quite a bit indeed. Now you do notice that the timing is off. It's definitely not looking very good as far as something reasonable. So what I'm going to do is not trust the simulation as it sits, and instead I'm going to go into graph mode and grab an analog graph. And so here we are, analog graph mode, and I'm going to grab my V out. I'll just toss it in here, and we'll set the stop time to, let's call it 10 milliseconds. Should be good. And let's simulate. Okay, so yeah, something's definitely amiss. We're getting huge transient spikes, and I think I just spotted. Is this error number 4? Um, that capacitor, is definitely not big enough. It's getting loaded well in excess, so it's not dampening. And so our output capacitor, we said that we wanted 100 microfarads. And so let's give that another simulation, and there we can see it stepping up. And we don't have enough time to ramp all the way up, so we'll extend this out to 100 milliseconds and see how that works out now. Redoing it. Seems to be doing something odd. Let's just run the simulation and see what it does. There we go. It stabilizes about 12 volts. It's a little bit high. So we could try to bring it down. We can try playing around with the frequencies as well, and see if we can tweak it into something a little bit more to our expectations. Let's pick a standard value 6K8. See what that gives us for an output voltage here. Okay, so that's lower than what we expected, but it's definitely safe because the chip that it's going to run it, it'll operate down to 3 volts, but as high as 12. So if I'm running at 10.5, I'm okay with that. I can live with that for sure. And so now let's take this, stop our simulation, and we'll take a look at this on the graph to see what it gives us as far as noise. And so now we can see it's actually operating properly, ramps up to just over 10 and levels off. So this is quite reasonable. If we wanted, we can do a couple things to this. One is we could put a LED on here to indicate that it is working. We could also put in a Zener diode as protection in case there's any transients, or if this decides to go nuclear on us. But for the most part, I would call this design acceptable. And now the next thing that we would do is we'd start to look at the PCB layout, and I don't think we're going to get into that too awfully much, but we can start to look at how to start picking PCB part footprints and what have you, because you can see some of my parts are through hole, some of them are SMT, some of them don't have footprints, and so this is actually a whole another video that we could do, but I'm going to wrap this up. I think this video is probably long enough now, and I hope that you see that given a data sheet, you can definitely work it out. It's not typically that complicated to work your way through these design applications. The trick is just that you need to read the data sheet and maybe do a little bit of research into application notes. All right, so we'll call that good enough, and I hope you enjoyed the video. If you do, please give it a thumbs up, and subscribe for more of this content as I work through some designs here and there. All right, thanks, and have yourself a great day. Bye now.